system. This is really where economic engineering shines. There's some aspects you can model doing that. Although they may appear to be totally trivial for an engineer with a second order system from looking at you. I mean, I can clearly back that out in my beginning of controls courses. It's nothing special, but you will see the economic interpretation of what's really going on. That's where the difficulty lies, number one. And number two, this is also where the impact of economic engineering is, because this is something economists have a very big trouble. Okay? So to set us up for that, I just want to come back to this first order trend, what I call first. So these systems, I'll just call them trades. They're just buying and selling. Why do I say trader? Well, because they can either buy or sell. If this math is going to the right, maybe it's buying, and to the left, it's selling. Remember? Selling, what does that mean? With respect to this inertial trade. This is a market, this is a big, big market. There are huge price inelasticity, all right? And we're looking at all the demand with respect to this. So we're keeping ourselves to our Galilean relativity. We realize we cannot measure quantity demanded as an absolute thing. It always has to be relative. That's this guy, right? And he's going to interact with this market. This is the price elasticity of the agent. He is having his personal price, P. And he also has some desires or other things, or they're acting on him, incentivizing him, all right, to do something. That's its external force here. Well, this is exogenous, it's acting on him. If this economic force acts on him, the idea is, all right, how is he going to respond? Right? The response has to be either the demand or the change in demand or the change in this price level. All right? Yeah. This is called completely consistent with the way you would look at it as an irreversible mass. Right? You put a force in the ground, how does it react? Well, changing its momentum. And if you figure out what the change of momentum is, and you know the mass, you divide the change of momentum by the mass, and you'll get the acceleration. Acceleration is what they call the extension of demand. All right, the needs that go along with that want. Okay? You demand more or you don't. Now, how does this go? If this sample were not there, it will be this is the market friction. If it were not there, you will just start demanding more and more and more, and no problem. It doesn't really bother him. That's just what he wants. Okay? But now what happens, he has to, he is connected to this market. All right? So what happens is he is taking his desires and he is relaying them to the market. All right? Yeah? So this is mitigating his trades, right? But this thing is a source of friction mechanically, and it's also economically. Right? So this acts as an intermediary between the agent and the big market. Right? Now, what will happen? So if suppose that there's no external loss, and this agent just has a certain price level, then because of that, he will have some kind of demand. Because he is in contact with the market, he's just going to deliver to the market until the demand levels are equal. That's what's going to happen. So there is no, this is what we would call the free response. Okay? So F is 0. That's just like these. That's the he wants to. So this guy is otherwise free of any external wants, right? He's not free totally of wants. There are these brokers who are charging him something. That will depend on his price. All right. Now, there really, what's going to happen, if you know anything about mechanical systems, is that, well, what will happen in the long run? Well, in the long run, nothing is going to happen. It's going to, well, in the long run, this trader will take all the same quantity demanded as the market, right? If this is zero, then ultimately it will converge to zero. Right? So you're just brokering all these trades, just causing him to lower his price all the time. And at some point he'll just have the same velocity that this has velocity v star. And this, I believe that's this, I believe that's. So. Yeah, these are all the pre-response. Okay? The rate at which this goes is determined by the friction. Okay, so the little friction, now, anything will happen. That's what happens here. High degrees of friction. This was right. This is what happens. These are the kind of graphs you will see columns with. So they'll have these exponential decays, but sometimes they'll turn around and they'll have exponential rises, that kind of stuff. Right? Yes.
Where is the wall in this picture? So is that the x-axis?
Yeah, there's really. This is the momentum of. This is the momentum here. Something that was here. This is just the price of this guy.
Then it goes to sort of zero. So what is the 0 point? Is that the same velocity as the?
Well, now this is some p. This is p0 is at time 0. This is p. The price at time infinity. Okay.
You see. By infinity, it's sort of balanced with the wall.
Yeah.
Yeah. Okay.
Yeah. So at infinity, the velocity here, so the quantity demanded equals v star. So the demands are equal. That's what happens. And the agent acquires some price level, which is a long run. Probably Beer knows this best. This is what you would call the long run or the very long run. I get into the long run price level. Yeah. Right? So they have the short run, I believe.
Yeah.
The long run, and then a very long run. Yeah. A very short run. You never heard of it, right? So this will be the short run, right? Somewhere here. I don't know, until you're within a certain percentage. This here is the long run, right? Yeah. Okay. They'll make that distinction. Right? The way you figure out what the equation of motion is, well, you know how to figure out. You know that you're going to have a balance of lumps, desires, forces, right? So all you need to know is look at the balance of forces of this guy, right? If this is zero, then there's only have one force, which is that frictional force, and that has to be balanced with the change in price, right? If you work it out, you get this equation, right? If I set this equal to zero, we'll see that P naught is equal to minus gamma P, and then we get the solution, right? Now, how would you read this equation from an economic point of view? So this is the rate at which the price is changing. This is the price that you multiply by the discount rate. The discount rate is precisely equal to what we call the damping, right? So what's really happening here is that, and if this is zero, then these have to be equal, okay, with a negative of each other, right? So this is a sort of a percentage per unit of time of the price. And you see, that's what we call a discount. Right? So the broker here or the intermediary, what he does, he says, well, I'll do this trade for you, but I'm going to charge you a percentage of your price, the price level. Okay, that's what they do. Okay, that's what we call a price discount. per unit of time, right? So we take off that was cut, then what's the broker's cut? The higher is B, the higher is broker's cut. Okay? We are a little bit more familiar with may find this a little different in terms of position Q, but that's okay. We can figure that out. No? Because this is equal to F times Q dot, you know, and this is M times Q dot, and then you know. That what it's really saying is M Q dot B Q. I wanted to keep it in terms of the price, because that's how the economists will think about it. No, a lot of the economists, especially neoclassical economists, argue that agents instantaneously react to a change of circumstance. Okay? And this is the idea of demand. So, you know how we have these crossing things and this is the equilibrium or whatever it is. Well, this would be that P infinity level, right? But their idea is this happens instantaneously, junk, right? And this was not found to be true in the 20s and the 30s. They had this thing called the Great Depression, and prices just wouldn't converge to the equilibrium value for a long time. And there was a guy called Keynes, and he came up with a new theory, and he called it price rigidity, which is the tendency for prices not to move immediately at equilibrium. So here I plotted the price rigidity in terms of the negative transfer function. Okay, so you see, you have some outside effects, an exogenous effect, and then you look at the price reaction, but that goes with a certain delay, you know, actually it's not a pure delay, it's just this exponential approach. Okay? And so the transfer function here is the thing that models the price rigidity. Okay? And there's a lot argument in economics that this should be done, because you would think that you should be able to arbitrage this. If you know the price is going to be that in the long run, you should just like take advantage of by doing something. That can this be? But from an economic engineering, it's pretty clear why, because you can't do that advantage, because if you did that, you would have to pay all these transaction costs later, right? So it's just a function of the fact that you have friction in the market, you know, that prevents you from doing that. And so your optimal solution will exactly be this. And then we know nothing that can induce you to immediately adjust your value, and somebody else who is subject to the same friction costs, so the same transaction costs, will also not be able to arbitrage for it. Now, many people who have less transaction costs, so you see that a lot of them, security market, also in the goods market. So big grocery stores like Albert Heijn, you know, they can negotiate very, very good prices with the shippers, Bol.com also. Yeah? So their transaction costs are lower, so they can indeed grab some of the business of somebody who has very high, you know, transportation costs. Yeah? And that's true, because there will be another massive with a lower damper, but we going much slower, and then you can, you know, kinetic energy before he gives it away to a broker. Okay. Clear? What we're doing here is just kind of reinterpret. This is a very simple system, but it's very important to try to think through all the consequences this has. Yes.
Buiten. In mijn gevoel, als je desire 0 is, dan is het F0.
Ja.
Zou dan de prijsverandering ook niet?
Nee, want je hebt hier toch. So the question is, if this is 0, why are you changing your price? Okay.
Because the market is changing its price.
Yeah, no, because the market, you're still interacting with the market through this intermediary. That's affecting you. You know? You see? You see what I mean? Yeah. Yeah, if I had cut this thing, or if B was zero, it would be right, then nothing has happened. But then this agent is being subjected to some incentive. But at the same time, he is interacting with this market. So you need to have that the sum of all these forces. So F plus this force, the frictional force, right? Which is B times V, right? Plus P naught, that is zero, right? Okay. You see? This is what Newton's law is telling you. So it says P naught is F, it's a mindset in this case, which is it's a counter force. Doesn't matter. So this will be a mindset. So it's telling you this F is the sum of these two. Okay? When you take a free body diagram, then you'll see that. You have to take, so you might put another element here, you'll have to have that thing too. So you'll have an inventory, and that thing will also provide some kind of desire of why you want to store it or you get it out of there. Okay? So the whole thing is set up your free body diagram. And the free body diagram, you can also see that as a price clearing mechanism. Now, what is a free body diagram? It just looks at the change in your price, and it adds all the forces that are acting on it, right? All the incentives and wants, and that has to balance, right? What does that mean? That means that you can also see there's a sort of clearing mechanism, and this is just the price clearing, right? So the price has to adjust so that everybody's desires are precisely balanced, okay?
You just mentioned the brokers. If your desire is very high, so you're all buying and you want a loss, you can change your gamma depending on buyers.
Now the gamma is determined by the broker and by your elasticity.
The broker knows I want a lot, he can give me a different. So,
Yeah, then he will change his B. But he won't be linear. Okay? Because all of a sudden he will give me a discount or this. So he will change his B, or he may charge a flat fee up front. That's also not, because then his force will be B plus some upfront cost, which is also not linear, right? Because what's this thing doing here? Right? Here I've limited myself to linear things, but you don't need to do that. So if you have this friction like this thing, I mean, of course, first nothing happens, so it's like an upfront cost. Okay? Okay. Now, these are good. This is a good way to think, So try to play it in your head so you can see linear friction is a little special. Usually you'll have an upfront cost. So that is, how you do friction first, like you're standing still friction and then this other thing. So that's the upfront cost. That is the difference between that. Get the thing going.
so your mass is not.
Oh, you mean the normal force? Yeah, well, that's not the case here, right? It is a little bit different. But you could imagine that there is another sort of friction that depends on the prices, right? I haven't thought of that. Okay. But it's like mechanics. Every time you just have to model it and taking these linear elements, I'll be kind of just so used to it. Right? But conceptually, all of this is fine. But then you won't get a linear differential equation because you'll have here another constant, You have to deal with all of that. But the important thing to see is to get the feeling, for how this, what this all says, okay? But the math here and the engineering is too simple to mention all that. So what's difficult is to really understand the economic impact. So what you're doing, Well, this price here is really with this person. Have nothing to do with this person's price. This one doesn't even have a price. He just makes a cut. He has no demand of himself. So this intermediary, he has no price. He won't offer you a price. He will just offer to ship it for you, right? The other thing to see is that, you see, if you know the price of necessity, it doesn't take long to figure out what the discount rate should be. You know, all you need is to know this, all right? With a few data points, you're pretty quick at determining it. Now, the way you guys know discount rate is probably what the ECB charges on overnight money, something. Okay? But economists, especially Hicks, I think, and with Keynes too, they imagined a discount rate for every good. Okay? And they call that the own rate of discount. Now, this here is the discount rate only for the goods that are going to this GQ, right? Okay? Some other direction, the damping may be quite different, or the math may be different, and you will get a totally different discount, right? So this is not the discount rate, meaning for everybody all the time. This is dependent on the goods in question, on the demander, and on the intermediary. All right? Huh? Every situation has its own discount. Okay? There are equilibrium situations that if they're not equal, then you can imagine them trading, which effectively will make everything equal, but that's a different matter. That's a matter of making a model of a complicated system with all kinds of interactions that you see the whole thing on some average down, okay? Yeah? That's not what the business is here, okay? All right? Yeah. Here I put in, I made this a step, huh? I took this, to make it a step. And you can take this to be anything at all. Sinusoid, that's what they call seasonal demand, you know. I just put it in a step, otherwise you get, right? So when you look at a step, you can ask yourself, well, what happens in infinity here, right? Good. So, actually, keep the paper that tells you what it is. You can check it out here, right? The attempt you get this to be the yeah, so it's going to be divided by gamma, right? The one divided by the discount. That gives you the long run. But this thing here, the want, the external incentive divided by the. Well, that's a long run price. It's an interesting result, right? I look at, I'm looking at you here, and we're back to us talking about all these long run prices. And most of what he had was personal systems. You can immediately determine what this thing must be. Well,
Yeah, this is exactly the same as the example thank you where he looking at aggregate demand and how a shift of the aggregate demand curve, which there will be a shift of the reference frame.
yes.
That affects price.
Yeah. Yeah, so that will shift the curve. So say they will do, I did have a new reference frame that is, so what they'll do is what we do is we do the analysis always from this reference. So then you just see it doing the dynamics. But they attach their reference frame here and they keep shifting the reference frame, you know. So you get some kind of, you look at that. So they look at shifts on the demand curve and they're really shifting the reference frame all the time rather than looking at the dynamics. You can do that, right? It's a crazy way to do Newtonian mechanics. Not so crazy, actually. There's a way of explaining Newtonian mechanics that this thing is also a shift of reference. All right, so then there are no such thing as forces, only shifts in reference. But that's not the way we think about You know, and that's why we have the minus sign, even. You know, but that's not the way we like to think. We like to fix our reference frame to something that we really know the velocity is constant, and we call that an inertial. And then we set up the equations of motion. This is just a reference frame whose velocity, whose quantity of matter keeps changing. So then you're always going to see some fictitious forces that are equal to minus F. You know, okay. So that's the problem with their analysis, is that their reference frames are not inertial. So they have to keep shifting the demand, right? But you have an inertial reference frame that goes to the 0 point. The 0 point is inertially determined, right? It's there. And if you don't do that, you're going to shift this thing around. Like this, because the point of 0 is shifting. That's what Mankey does. Yeah, from our perspective. Right? You guys follow that? Huh? You know, so you can be accelerating and thinking that you're in a reference frame, but you can do that. But then you sit in your airplane and then you get pushed back. So you say, "Well, I'm standing still, but that chair is just pushing me." You can do that, right? But, yeah, do it. And then you got the same equation. And then you have to. The problem with that is you have to keep measuring all the time what that force is that's pushing you. You have no way of predicting it. You're just sitting there measuring this dumb force, right? Whereas if you say, look, the world is standing still, it's going at a constant speed, and now I can say, well, I'm changing my, model of this stuff. Yeah, that's an interesting remark, because there is a version of, there are several more philosophers of science who have analyzed it, who said, well, in a sense, it's all about the first law. The second law is already a change of reference. That's the idea that Einstein took. He said, well, an object in gravity is also really inverse, and it's just a curvature of space. Changing the reference. Huh? Anyway, more philosophical than engineering. We just want to do F is P to R. Yep. Fix your reference frame. But is that economists always shifting the demand curve at will, shifting reference frame. Fix your reference. Otherwise you get confused. All right? So there's a couple of things here. Also, this kind of system and control perspective, right? So that we take something exogenous, that's the input, right? And then we take something endogenous, which is the price, and then we plot it over here, right? So that's what I done. You see? So instead of just writing down these equations like some physicists, this is the way we like to think about it. Then in calculating between these two things, we can give it nice names because we call this the benefit. Now this case is about functions and alternative evolution and whatever it is, right? But that doesn't matter. It should be an awful. So I call it a transfer function because you guys are all easy to lost it. It's not. It just takes its F that goes to the speed. That's the right. Now we go a little bit here. You see, this is also this typical economics approach to a new equilibrium value. Except what happens here, this is an endogenous thing. So this P is endogenous, the price is endogenous, this output. So this behavior here is endogenous to the system. You don't have to explain. You don't have to tell it to do that. You just have to put the step on, right? Now, Barrett, you know this, that when they model these exponential, they don't do it endogenous. They impose this behavior exogenous. All right? You see? So they say this agent, we model the agents as if they do this. Okay? And that's the growth. Okay? And then we measure this. Okay? We fit this. Okay? That's not like do it. Okay? That's you nodding. That's precisely how they reason. It's very important to see the difference between that. Okay? This is a signal, this is a function. And that's the thing that comes out of here. It's not something you impose on it. Okay? The only thing you impose on it is this incentive. Okay? Then it decides itself what to do about it. Okay? So an economist looks at population growth or capital growth or whatever, right? Output growth, price growth.
And that's what they call the very long run.
The very, yeah. But either way, they just say this is our model. Here, move. This is development. This is price stickiness. So they don't go through the whole modeling of having an intermediary here. And that's what you need to do, right? When you look at something, you see they have an exponential approach. You say, well, not that first order system. Anyway, good. Good. All right. Good. Good. So the problem with this kind of business is it all looks easy and but it takes a while till you see the subtle differences between this Newtonian approach and just a regular way economists are looking. They just don't have the concept of a force, right? So they have to solve it by assuming the solution as being the right one, you know? Then they just brand me about the solution. Okay? Immediately write down the equation of motion. Good? Yes.
Physical system can break if you apply too much force.
Yeah.
So something that also
Sure.
Yeah.
Yeah. We come to that in the next thing. Here you can imagine that you're going to crash right against this wall. Even if they really cannot break because of the damper, you can't really break it. I'd like to do that in the next. Yeah, you're sure. But to answer it really generally, it's just a nonlinearity, right? Or a change in parameters. If something breaks, then if this thing breaks, then what happens is this V changes. Maybe it breaks, the V goes to zero all of a sudden, right? And it won't be dampened. It's got to go up. You see? It's not that really break. Okay? Not even in physics. Right? They can break it in two pieces, but that doesn't, there's no law of conservation of mass, right? So you're not going to get rid of it. Right? But the damper, the break is just, in this case, only the change in that B. So, you can also imagine the say crashing against here. And what will that be? Well, that will be an enormous force, very desire for you not to join that market, you know, or how, you know, you have to model it. But for us, it will be the molecular forces, you know, when these things get close together, they really, you know, but you have to also assume that this is not a, you know, nobody's saying this is not some kind of gas with a high mass with just go in and it's nothing. You have to do some extra modeling. Hyperpatch collision. Yeah, so maybe I can't answer that either. I would just say that there will be a change in the here. There's not much that can break here. You have two masses, they can break. Only this thing can break. Well, you can break this and you'll just have two agents. You know, the path go in their own. I guess you can do that too, right? Or one person split in two. Yeah, that would be what you do. We want to get a better quality out of it. It's more faster. Just explode it. Yeah. Yeah, that'll be a break. In the total price of our system will have to go positive price laws on. Again, yeah, now we're just doing linear systems. There's no reason not to. So, all right, these are all good questions. It's good to go through your mind and leave. So here it's like we see also that when you keep applying, well, there's no limit to how high the price will go. Right? That's something that is weird. Right? I think you have an economic situation where somebody is always increasing its price no matter what. You will never have equilibrium. So poor Adam Smith imagined that everything had a natural price where it would go to. Remember that quote? Right? Obviously, that's not happening, but it says that when the damping is different, the B is very, no, the little bit of friction it will go. It will take a little longer, right? Or much longer, but it will always go to some price. That's divided by gamma. But if gamma is zero, this thing doesn't exist, right? You can't put in zero here. All right, we'll just keep going for it. This is just an interesting point that you just got to appreciate that. It took a long time for people to see that because I think I've said this before, but I'd like to make the connection again. That Aristotelian mechanics, they used to call it before Newton, they also had it that this couldn't happen, right? This couldn't happen, it's ridiculous, It's something we just keep accelerating. And they had a feeling, they looked at things falling and things rolling, and they all realized that everything comes to a stop, right? And well, they would look at planets moving around, but that was celestial. And everything kind of came to a stop, and they would try to look at the tendency for achieving kind of, they would categorize things depending on how high the speed of infinity. So if you drop some brick, or if you drop water, or whatever with a different shape, it will go with a different terminal speed, and that will have a different terminal. But it's just a hard step to realize that a body at rest goes at a constant speed, and as long as you have a constant force like gravity, the thing is just going to keep accelerating. There will be no stop, right? And there's no price equilibrium. There's no momentum, no equilibrium. Right? That's how P disgusting. That's disgusting. All right, so now, of course, with a massive body is the relativistic mass will increase so much, so you can't go faster than the speed of light. But with a photon, there's really no reason why you can't just keep going. The point I'm trying to make is there is not necessarily a natural price. If there is, it's always determined by. Damping always implies some form of friction, which always implies some form of dissipation, entropy production. Okay? And that's why I associate the natural price with the invisible hand with the second law. You always have some type of it, right? It brings things to us. Okay? And without it, we won't have. Okay. Take this one step further. We got a second loop. So what do we have? We have this agent. You can still use this intermediary, but now there's also an inventory. Either the market uses it, or we use it out. Right? It's another agent. It's inventory. You can store it. Okay? Now, this is sometimes what we call a dealer. So a trader is everybody. But if you have a dealer not only has a price, but he also maintains inventory, right? The consumer, for instance, only has a price, they don't have an inventory. A pure producer also only have a price. They just produce, they don't have inventory. Real producers do, of course. Real consumers have a pantry, but the economist producer doesn't have it. The dealer will have it, right? That's what you call a dealer. So a dealer has both an inventory of things, like a car dealer, right? The inventory of cars and right? This inventory has some kind of level at which it likes to be, and that doesn't happen, right? Just like any old spring, it just has a level at which it won't provide force, okay? And if you extend it, so if you go long, then now it will try to go back to its desired level, inventory level. And if you shorten it, if you go short, it will also come down. So the spring, the storage gives you notions of being long or short, okay? Long or short what? Well, your design. So you can imagine we have a project with Shell and they have these oil tankers and there's a desired level, okay? And they say we don't want to go above, and the more we go above, the more higher our desire to go back to this desired level. And there's some level where you just feel good, right? That was built into this, okay? So this thing, here you have this convenience force. And how much? Like this one we know, it's friction force, right? Depends on the flow of traffic. As you know, this intermediary doesn't store anything. He doesn't care. He's not storing anything for you, but you have to transport it. So he's look at it. All right. And you have this force acting on it. That's the exogenous incentives. And then, well, we all can set it up the equation and the price clearing. The price clearing is just as you add up all the forces and you set that, right? And this is your price clearing. In the transactions in this little market here, there's a price clearing effort, price clearing mechanism going on, and you can find out what it is by doing a free-body diagram of this agent. Then you see that the sum of those forces has to adjust the price. That's what we call clearing. Right. Cool. Now you all know that if I plug all this in, so I plug this and plug it, I can get an equation like this. Okay, second order. So what does this say? It has a Q, it has a changing Q, and it has the Q, the changing Q, right? What is Q? That's the inventory level. That's this thing. Right? Don't, this one has a velocity, and it so happens that because we attached it, that this is equal to the change in inventory. But you don't have to do that, right? If I had done this, an inventory, and then another intermediary that brokers the trades for here for the inventory, and this one is the level V, but this is Q dot, then this is not, V is not going to be equal to, right? You see that? Yeah. It's a big mistake to always assume this is the case. It's often the case, but only if you explicitly say it. This V here is your price divided by elasticity. That's what that is. That's your quantity of lead. And it is not true that all of the or supply goes in inventory, it may go somewhere else. You see? Is that clear? It's just too easy to write this down and to forget what V really is. V is just price times the price. Right? Clear? Now, if I now look at the input-output relationship, I still have that incentive here, that comes from exogenous incentive. And what I'm going to do now is look not at the price, but I'm going to look at what is in this inventory here, right? So I'll call this transfer function now the inventory rigidity, okay? Right? I'm not going to call it the price rigidity because it's about how the inventory reacts then, right? Now, again, I will look at the free response and the step response. And what I've written down is that these equations are almost equal. You can compare them to these, right? This order. That's the way it's done. To find something that economists would call a discount. This is here. Just that my discount factor is going to be a little bit more complicated. That's all right. Then I want to isolate what's special about the situation, and at the same time show what is the same. So you're taking this, your inventory level at time t is your inventory level at time 0 times some factor depending on time. That's how you sort this thing out. Okay? That's the previous plot. And in the step response, there'll be this 1 minus this. Okay? The only other thing you have to see instead of f divided by gamma, you now have f divided by k. That's clear how you get there. Yeah, because what happens in the long run? So all of these things have to balance, right? P naught has to be 0. You quickly figure out that this force is precisely balanced by this force. If P naught is 0, then the velocity won't change, right? And we're standing still. And then this force has to balance the force, right? Oh, there you go. The long run, right? And in the short run, it's going to do something. Bit more complicated because you see, you still have this damping right there. There's still a time. If you look at this formula, which you're familiar with, you already see it here, right? There's a bunch of other things. There's zeta and there's omega n, all right? And this omega n is what we call the natural frequency. You guys know, right? And what would that be? Well, it's going to depend on what your demand is and what your storage. All right? So you go through some cycles. Suppose there's no friction, you start buying, and your inventory goes up, you got too much, you go down, and it starts selling again, and you go, so you keep going and cycling. If you figure out what that thing does, this is the cycle frequency. Okay? You know it. That's why I call this the trade cycle frequency or business cycle frequency. Okay? So the moment you're an agent and you have a storage, you'll see that you goes. And there's no way for it. That's clear. If I look at a car dealership, and if you look at this person's lot, you know, first he gets too many cars, then he has too little cars, then too many cars, and little cars. He's not keeping it like this. Okay? Because what's the point of having an inventory? Well, he has to sell out of inventory, but then he's low on inventory, so he starts trying to fill up, he starts demanding to fill up inventory. Okay? That's what he does. All right? That's what your grocery does too. I put these things on the shelf, I have to get it out, and then they have guys running around, go get things out back, and buy from the supplier, and put it back on the shelf. And all it goes up and down, so you see these stacks, you know, see the price level below. Got the momentum, then you see the Q, right? So the momentum here, you got the grocery store, there's the shelf, and here will be the price. And then here, you see all the stack of these things, and this will be the Q, right? Now they don't vary the price very much, but if they were more than that, you will see this thing going up and down, and you will see this thing down, out, thing. All right? Okay? All right? That's a natural frequency. You can just figure out. And then you can apply this other thing called a damping ratio. And you just take your damping rate and divide it by 2, and all right. This factor 2, where does that come from? That's a little bit of an issue, but not really. You see, we'll speak later on where it comes from. But I'll tell you now, the problem is that we now have 2 things going on. Both price and inventory are changing and are being dissipated by this damping. Okay? Now, in total, they can't dissipate at more than a rate gamma, right? But if the surplus goes in the product of the 2, right, that means that if either go with half the rate and I square that, so I have the current squared or the price times the current and the force times the current, then I'll get equal rate. So it's a consequence. This consequence two is a consequence that we have second laws. So we have two state variables and it differs in both state variables. Okay. Right. You go over the evidence, and you see this is a rate and this is a rate. Okay. So this is 1 over days or seconds, and this is also. What you do is you look at the ratio of the two. Who's, are you damping faster than you're oscillating, or you're oscillating faster than you're damping, right? Okay? That's that thing, okay? You divide by 2 because you just want to look at one signal. You're only looking at Q, not at P, all right? Okay? Well, that's how you can kind of read this thing. You see that? Huh? This is a little bit of intuition. So with discounting, cycle. You want to know how fast we're discounting with respect to a cycle. So you can think of the cycle rate as your clock. Yeah, that's the thing going around. The quite typical business cycle. And you want to know how many transaction costs do I make within a period of my cycle. To affect everything. If I lose everything in one cycle, I'm not running a good business. I'm more of a consumer, right? If I can keep cycling without losing too much in transaction costs, then I can buy and sell and buy and sell it. Otherwise, I just eat it all up. That's what we're going to see. So I call this the discount propensity. So that comes from this idea of consumption, right? So the friction is also consumption, right? So you get rid of it. Somehow it's consumed and dissipate, right? And then we talk about the propensity to consume, all right? So there's a tendency for people to consume the resource, okay? And did want to use consumption because it's a little broader. This could be any trade. It doesn't need to be consuming. But in a sense, it's consuming. This is the consumptive allocation. Also. But right now, I just call it the discount propensity. We call it, of course, the damping ratio. Right? This one is that. All right. This should all be familiar from your mechanics. What it is, right? But you got to kind of go through the exercise of internalizing what these things mean. Okay? But so the moment you're talking about business cycles, you already know this. Okay? Somebody's got to have demand and inventory. So in your work, he goes to the, when does he do these cycles? The business cycle. He calls it the business cycle. Just actually just part what? Part 2, 3, I don't know. Part 3, yeah. There he starts talking about this thing. From our perspective, he just added he's just got both storage and demand. Otherwise, I just don't see how you can get a second. You got to have 5 springs and make a single system. You need to have both. Right? Yeah. And then you'll get oscillations. I mean, it's kind of given. Yeah. Right? Now, in fact, you guys already know what you can look at. See the way one of the tools are. You'll see exactly the rate of these business cycle. Well, trade cycle. Right? And you'll this.
The damping ratio or discount propensity, could I see that at the sort of amount that is dissipated per cycle?
Yeah.
So sort of the consumption is applied.
Yes. So it's about discounting the price, you see. He also discounting the stock, and that's where that happens, right?
Yeah, so it's a ratio between the amount consumed and the amount in rotation, right?
Yeah, in circulation. Yeah. Right? So what's in the business cycle, that's in circulation. Huh? And it's actually the rate at which it circulates and the rate at which it's consumed. Okay, that's what you do. So you know, intuitively, what you want to see is that a trader circulates much faster, rotates much faster than he consumes. Okay? Buy and sell, and he tries to make very small transactions. Okay? So we will feel already that it's an underdamped system. Right? And a consumer is, of course, the opposite. They don't want to go and buy and then go back to the store and say, I didn't want it, right? So the consumer is going to consume much faster than the author. Everybody doesn't even bother to go back and restocks it. Right? It's sort of, you have these consumers that buy something on and then send it back. The company's trying to get rid of them. You know, we're charging them a lot. You know, it's that's big example, right? So you crank up. What you're really doing is you're cranking this thing up so that it doesn't become so much fun anymore. Well, that's the feeling, right? So you see that these traders, they fall into three different categories, okay, depending on this discount propensity. If this is between 0 and 1, you expect more dealer-like behavior. And 1, you expect kind of a discounter, right? There's also, and the higher one, you expect consumers, okay? All right? And we can all classify them as discounters. So when zeta is 1, then you would say it's exponential. It's just a regular discounter. Whereas below 1, you would call it a cyclical discounter. So what he's doing is going through highs and lows. You know, cyclically, he ups the price when he wants to buy, and he lowers the price when he wants to. No? All right. Yeah, that was good. So he keeps changing the price depending on whether he's buying or selling. So it goes through a cycle of this discount. And we'll see that the other guys, the consumers, they are hyperbolic discount. Listen to the next slide. This is also our last slide. I'll just take a really long river here. I believe this. Oh no, it's not much. One more slide. So really, I did all of this talking before I even looked at the graphs. But we got those graphs, and it was good, but it forced us to go through it. Okay, and microphone working, good. So let's look, we did it all just in our heads, but we can take a look at it, right? So here's the free response again, and here's the step response. And you can see that, so when the propensity to discount or consume is 0, that just means, you keep going up and down, right? And if you get a shock, you just go up and then you cycle around there, right? So you never really achieve your desired balance. You just keep going around with maximum amplitude, right? Okay. Now I crank up the damping a little bit, the friction. Well, you guys know what's going to happen, right? So it gets a little, it starts dampening out, right? So that it gets modulated, right? With an exponential modulation that goes e to the minus gamma over 2t, right? Here's the over 2, because we're just looking at q, all right? And the frequency also changes, right? So you get this omega d is omega n times square root of 1 minus sigma square, something like that. Okay, actually it's on this slide. So this is the solution, this is what you get. So you see that what's happening is you get a regular kind of exponential discount, and this is what happens to the other half of the exponential discount. It either it starts splitting itself in a cosine and a sine that are combinations, okay? It's kind of interesting how that works, right? And then the frequency, and then also the frequency gets modified, so it gets a little bit stretched out in frequency, right? Yeah, the reason is that if you take off like omega n, at a certain point you start delaying yourself, so yeah, you'll make it, but the wavelength gets a little longer, all right? And then if the zeta is 1, the wavelength is, well, the frequency is 0, so the wavelength is infinitely long. So that's the point at which it takes you, in one cycle, you basically dissipated everything, okay? So you don't have enough oomph to make it through another cycle, all right? So then when you're one, there's a sort of a transition thing, right? So you're both a consumer and you're a business, okay? That's an interesting situation. So you're somewhere in between. So there's this cosine becomes one, right? So it's also kind of a cosine, but it's the cosine of a very small angle. Why? Because this omega d becomes so small, right? Huh? You see? Yeah, very small. But you can approximate the cosine with one, yeah, a very small angle. So if this is small, right? So this is very close to zero, yeah? But this thing is small, and you'll see this thing is approximately one, all right? And then similarly, this one will be approximately equal to omega d, and then you just cancel that out, and you get this, right? Omega d times t, right? You got a linear response, right? Don't forget that. So you can ask yourself, where the heck does this come from? And the reason it comes from is that, you know, what the philosophy is learned. So when the quantity demand is going through this cycle, you know, they're exchanging thought for quantity demand, right? So when we're going fast, it has a low amplitude, it's slow, it has the biggest amplitude, that's the start. But to the zero, and no velocity, so it's not making any transaction costs, you know. So although the transaction costs are high, it's not doing any transaction, it's just everything is stored. So from that perspective, this thing is just behaving like a free particle. Right? That way you get at this speed. That's what's happening. So it takes off with this thing, but then quickly finds out that things are not going well. Some details. Now, this when you set that bigger than one, the usual way you write this is there's a bunch of exponentials, right? Two exponentials. I think I like it. Try to write this. Because you kind of see, you know, the cosines and you see kind of a pattern emerging. Okay, so this we said was sort of a sine too, a very small number. You see, this is a sort of sine, a hyperbolic sine, and this is also a sort of a sine. Okay, it's a nicer way to see what's common with these things. Okay, the other way you can see it is that if you let this thing go bigger than one, then this becomes a negative number square root. You get an I here, right? Yeah. And what's the cosine of an imaginary angle value negative is molecules, right? Then it's not like to do this. Then it's kind of like this. Isn't this what happens? Right? So it also goes through a cycle with a hyperbolic cycle. And you can classify these traders as being cyclical, which is the typical dealer kind of thing, business thing. This is also what they call consistent discounting. So in economics and finance, all assume that you should have this, otherwise you've got a problem. Right? Find that where. You can explain it different away because they just never look at cyclical things. Right? But this one, they have a little trouble explaining away. Okay? Because those are the two real poles. All right, so you can really see that. You know, even if you think we have no cycles, we took out the cycles. Okay, and they call that hyperbolic discounting. You can look it up, and it's a big topic. Well, why people do that? And what appears that people like. Okay, so you always prefer a reward earlier rather than later. And that's clear. So I prefer a euro now than a euro in a week. All right? But if that is the case, you would imagine, or at least the economists imagine, that if you get a euro a year from now, you would prefer that than a euro a year and a week from now, right? Or even 10 years. And people, the same preference does not exist when it's far out in the future. Understand? So although today, if this were 1 million or 500,000, they want the thing now, if it's after 10 years and I get so if I promise you 500,000 today or 1 million today or 1 million or 2 days, in a week or so, maybe, you would react quite differently than when this is 10 years away. What's the difference? It's all far away in the future. So we tend not to, and the exponential function is not very nice at this because independent of where you are, it always looks the same. So you will always be discounting in the future the same way you're discounting at this moment. Okay? Now, why would you want to do that? The theory for that is that the theory that's usually used is kind of interesting, and it comes from our survival, right? So you have these hunter-gatherer types, and then they got some food, say they shot some animal, and then they can either consume it now, or they can wait and consume it later. All right? And what you see is that there's a tendency to consume much, much earlier. Okay? And eat yourself really full because you don't know what's going to happen in the future and all of this, and at least you got it, right? And this is called hyperbolic discount, right? So it's called impatience. And it's considered that it's wrong, but I don't think it's so wrong because let's look at it from an engineering perspective. So what happens here? What happens in an open-dam system? Well, if you look closely, I don't know how good these graphs are because I've done them at X. It's really bad to make good graphs. Right? Now, everybody's dwelling. Right? Now, this thing may not be correct, but you know this, that if you have an open-dam system, so here, this one is the birth critical dam. That's green, right? This is critical, this one's open, right? Well, it's an open-dam system. In the long run, it goes much slower. But in a very short run, it takes off like a maniac, right? Did you know that? So a car has this, right? So in a car suspension, you can have these things more, put it on a race position. And what you're going to feel is the big bumps, you don't feel them, they get damped. But the little bumps, you can feel them actually, because the system reacts very on the very short term, but not on the long term. All right? Overdam system. So overdam system, they go very fast for a short time, and then for a long time, very slow. All right? This is precisely this kind of hyperbolic consumption. Right? So you consume enormous amount in the beginning, then the other good example is when you stop at a traffic light, right? Now, if you want to stop at a traffic light, what do? Are you going to go do that underdamped? Well, no, because you'll blast through the traffic light, you'll put yourself over it, right? And try to roll it. So you got 15 tickets, right? Nobody's that's addiction. Okay? Now, the other thing is, okay, so what I'll do is critical damage. So, that's the most efficient way to get there. Right? Now, why would you do that? You know what people do? They first push really hard on the brake for a short period, and then they cruise it out. You come to a very slow rolling stop, and when they have to stop, they can just stop with a small low momentum. Right? That's what you do. Right? First we say the kop eraf gaan. So you first do a good brake, and then so you are overdamping the system naturally. Why? Because you don't want to have any surprises. Right? It's perfectly rational. It's little. All right? So these kind of things give you a good way of designing economic systems as well. I mean, there are many times, especially with consumers, it's reasonable for them to want to consume early, because they're very high transaction, storage costs, I don't know what. And they like to avoid that, and then they just quickly consume it. right? Now, what would you use as a critical distance? Well, I would say that's the first type where you don't really have oceans, right? So if you're filling your shell has these oil containers, some of them they want to fill to the brim. They can't overstock because, like a gas tank, right? I think that's in the paper. If you want to fill up your gas tank, you want to do inventory management. You definitely don't want to. You don't want to go over and another thing coming out, and the guy, coming out at you or screaming at you, and all that thing we don't want. But you don't want to be standing there forever. And you can first put a gush in it, and then it goes really slow. I once stood in a pump that did that. In the beginning, you did something, and then it was slow, and you go crazy, right? So what you will probably do is actually this, right? You will try to get it as fast as possible, right? And then at the very end, you have to pick that back a little bit, and well, that takes switches on itself. So you can use these kind of things to do an inventory management system. Like, what is your inventory? Is there a really, like a gas tank, is there a limit to how much you can put in? Then I definitely wouldn't do this. If there's no limit, it's much faster to overshoot a bit, right? So do you get this rise time to be really short, and then the settling time, you can optimize for settling time, and then you overstock a little bit, and then understock, and that's fair. All right? Yes.
In economics, don't the desired inventory level often depend on markets? So your
What's your inventory? Okay. This is some inventory gap. This is me with my thing, right? Subjective to forces. That's all it is. You see? So what do you mean by depending on the market?
so a dealer goes through cycle,
Yeah,
but he has clear infinity, so from level over which it oscillates.
yeah.
Would that then be sort of its mean inventory level of? Well, I understand the shell example where you have like higher level of fulfillment of the tanks or a max.
Yeah, you see, this level is exactly F divided by K. That's what you see. So it's not the design level when this is zero, then you go at the desired zero level, whatever that is, right? And that will be it. Right? So this is the zero level. Okay, so I think this is a good question. Let me try to answer it. So the question about if you just take the spring off as a separate element, well, there's nothing active, right? What is its desired level where it wants to be at? Well, that was whatever this is, I'll call that zero, right? So what happens? So here's that zero, here spring force, and here is Q, right? This is clear. What if there's a force acting on this guy, right? What will be the extension? How long will this inventory go? Like, force here, right? This will be that force, right? All right? And that's what happens here. So you put this, if this force is zero, the force is going to go back to the zero. Right? If the force is not zero, it's going to go to the level Q infinity, right? And what the external force equals the storage force. At that point, the change in momentum velocity is zero anyway, because this thing is going at the same speed as that, because Q dot is zero. Now this thing falls out, and you need these two levels of the So this here will be F divided by K. You see? All right, now you can also have divided by K, except F is zero. All right, that's the answer. You see? So what happens here is this tank is your inventory is empty, or is you call zero. It may not be empty, but it's some desired level. This external one, the inventory will slowly converge to a new level at which it will remain. You see? As a consequence of this incentive, right? So this incentivizes the trader to store permanently an amount, a certain amount of units. Okay? And that's how he balances the incentive, by providing a counter incentive, from inventory, right? In the same way as this, if you take this away, it will get balanced by a counter one from the broker mitigating trades. Okay? That's what happens. All right? Okay? I'm going to read this. So, in this sense, it's an inventory management system. So it's saying here was the old equilibrium level. This is a new long-term equilibrium level. So you have no damping. You will never achieve your new equilibrium level. You will always just cycle down. Okay? A little pendulum right here. This is old equilibrium level. And if I go like this, it will try to go to back or to a new one, but it will never really reach it because there's no friction. It will just go cycling. Okay? That's what the problem. Okay? Now, if I have a pendulum and I put some big magnet here, it's going to go whoop, 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 and then tip over there. Right? That's what happens here. So put a step. In a sense, I call this an inventory management system. Right? Now, how this inventory rigidity goes is very dependent on this factorization, this propensity. Okay? Here you see just how it is. This is the formula that tells you that. So it depends on the first order system moment, it's kind of a steady discount, but underneath this modulation, something weird, something else happens, and that's very the qualitative nature of that is very dependent on whether you're a business, whether you're just a banking discounting kind of person, or if you're this is somebody who kind of loans things, right? So you will just ask interest rate, or whether you're a consumer. Either way, all they do is try to go over there. This guy is never getting it. And he never stops trying. Did that answer your question? Mm-hmm. So this is very complicated behavior. And a lot of it, economists really don't have the tools to add. Okay. I think Mankiw doesn't have, he has a business cycle, but it's not connected with the discounting theory. Certainly not second order systems, certainly no second complex numbers, everything is. Right? So this is really where we take off. And the other thing, what you should see, this is kind of super complex behavior. Specifying, you don't need to. And you just need this in 2 minutes. Nice. Yeah, because you want to do this, right? But to do that's how you scale the factor. Now multiply the whole thing. Okay? But the thing that really makes this happen are these two numbers, right? So if you want to model something as a second order system, you can go through this exercise, or you can take a quick look. So for instance, the economy has, I think, 4 businesses. Right? The inventory cycle, and the technology cycle, and the chondriatic cycle, 3 or 4, right? Well, if the 4 cycles well, I would say 4 cycles, what is it? 8 order system, right? We have 1 cycle, it must be an order system. Right? If I know the cycle length, I know a lot. I know what B, right? Then I have to look a little bit on how you discount, and then I have all the guy in, I have that, right? Yep. I put my parameters, BK, then with few pieces of paper, right? So what you do, and you know this, I mean, if you look at the poles of it, very well, I mean, you know, I'll do this next. Previously affected. All you have to do is get these poles, you know, how hard is that? See how powerful is it, you know? The difficulty lies in really interpreting this. It's very easy to get confused. What does Q means? What does P mean? What this is? What that is? All right. Huh? You know how it relates to economic modeling. You know, it's important to know, but it's also important to some point get the trust that the system just works. You know? So you'll be programming this as spies or something like that. And it does now work. It just works. Well, this is how you end up building these things. You just go ahead and plugging it in and then looking at the results and trying to interpret it from theoretically, you know. A little bit like an engineer will model any type of system. There's no question too much Newton's laws and stuff. You've learned it works, get it, and now just go this first order system, second order system. Oh, how many poles do I have? So many. What are the dominant poles? You know, it'll start. There's one thing that's cool about a second order system. Any nth order system can be written as a cascade of systems. Okay. Now, these are complex numbers are just complete. So you can write you can solve any algebraic equation using complex numbers. So if you take a Laplace transform and get an algebraic equation, you can solve it. Okay. So you will always have a solution, right? So, and you know that you can just count the pole pairs, okay? Right? So, I promised I would stop a little earlier today because of the simple class list of needs, and well, we'll do so. So, unless there are any more questions.
Ever group have like third order dynamics?
Sure. Yeah, many.
What does it mean?
Well, it would just be that this response is this transfer function, and you have to then you look at the transfer function and then look what you get, right? So how do you look at the, you know, first decide what is your exogenous thing, your input, what's your output? And then you just look at how that gets transferred, you know? And then you probably won't get something like this. There will be, if you have another damper in it, so your third order, that means second order plus the damper usually, right? Then there's going to be another discount rate, you know, modulating this, right? So you have, you have V1 divided by M, but you will have another damper V2, which you have to divide by M. So you will have two discount rates, okay? Well, this is one broker, this is another broker, right? And they charge something different, you know, depending what you use. Maybe we'll use a third order system, you know? So probably the cycle, you know, so you'll have, if you look at the planning, they have one pair, maybe this. I'm not quite sure how you have it, right? It depends. Maybe you can put the damper into one and you effectively, it will just make this, you know, increase the damping. It depends a little bit how you configure it and what you have. But it's no different than any other third and fourth order system, right? Now, if you have a fourth order system, and there are two alternators, well, how would it look? You will have two natural frequencies. So you have this thing, and you have say another one is twice the little faster. Those things going to happen. But you have a bunch of these, right? I mean,
Yes, so
you showed me one with a supply chain.
Yeah.
Right?
with the supply chain for each agent you add, you get a high order.
Yeah, so this is then one element in the supply chain. So what you do is you add another one with a last spring damper. That's how you do it, right? So you put them all after each other. So you have a beam that's like that, right? So every little section of a beam has a little elasticity, a little damping, and a little piece of mass. And then you just put them all together and you give it a hit so you get this traveling wave, you know? And that's like the supply chain. You see? So you gotta see, what are you gonna see on the other end? Well, I can see, pattern, right? If you want to see this kind of stuff, you will see it all damped out. Everybody's sitting there with his own inventory, and is also making his own transaction costs, and also exerting his demand on the suppliers and another piece of demand on his customers. And yeah, you can just model it like a coax cable. You know how you model that with impedance. I don't know if you've done this kind of stuff, but you just work your way through it. Yeah. But I know really great examples. Beer have a big model of the economy where you have different traders interacting, you just get fifth, fourth, fifth, sixth, I don't know. I mean, how high, what is your system? Huh?
I think I've added 4 intermediate feeder brokers. So 8. So that's an 8-1 opportunity system.
Yeah.
Something like that order, I think.
Yeah, but then it all depends what you choose as your input and your output, what you're going to see also, right? You can talk about the system, but also you have to look at what transfer function you're looking at, right? And then how that goes. And then you will see what this inventory rigidity, all these other things. There's all kinds of stuff here. These are just. So you see, the sky's the limit. This is the thing. Once you understand this, pour is a cue into somebody else, right? Who starts then pulling stuff out again. I mean, here this guy doing nothing, but you can imagine another person sitting here, right? This, right? It gets really complicated, right? And this is an already second order, third order, right? Third time student. 3 masters, right? 1, 2, 3.
Dampers.
2 dampers. Yeah, but it's 2 springs, so that's every.
And strings.
Yeah, it's 2, so it's like 6 plus. That's 6. This doesn't add 6 to it. These don't add to the order, right? If they come together in the spring. Yeah. You got so much better than I do. Come on. So you see, don't get too. This is a very simple thing, but you plug them together. If you make a function 9 and there's something else, this. I multiply them all out, and you put them in parallel, some of them, right? And then you know what the transfer is from there, right? But you can only do this if you have this kind of model. You understand that? If you just have some exogenously delivered exponential thing, how are you going to cascade these things? How are you going to put them in you'll start. You can't get anywhere. You can't build anything. All right? Okay, guys. See you all next week.